So welcome to the first session, which we shall devote to the solution of some problems in signals and systems. Of course, we have been all along, as we discuss certain concepts, giving examples. But it is worthwhile to spend at least one or two sessions occasionally in looking at the solution to some rather illustrative problems or problems which have special points that are not easily illustrated through normal discussion, right? Now, the practice that we shall follow in solving problems is that I shall first state the problem completely. Yeah, I do understand that there might be textbooks available and one can refer to a certain number and so on, but I think it will be better that we state the problem because the discussion must be complete in its own right, rather than having to depend on some other book or some other source to understand what the problem is. We shall state the problem completely here just before we solve it. So let's begin then by taking the very first problem that we wish to address. Also, in the process of problem solution, we shall treat these as tutorial sessions, and therefore we shall invite and actually expect students to come and make an attempt to solve the problem. Yeah, it is not, in fact, I don't expect that the student will solve the problem correctly every time. In fact, the student may not even be able to solve the problem completely every time. He or she might only be able to give certain pointers or go a little bit. But that's perfectly welcome. The whole point in a problem solving session or in a tutorial session is not just to solve the problem, but also to illustrate a thinking process. So it's important that we allow people to come forward and participate in the thinking process, even if it means that sometimes we might go along a direction that we don't intend to go, right? It could be a direction different from what would enable correct solution of the problem, or they illustrate new ideas, so we must allow that freedom. So therefore, I would encourage students to come forward when invited to attempt to solve the problems. Yeah, it doesn't matter, even if you cannot solve it completely, it doesn't matter. What is worthwhile is the attempt, not the complete or the correct solution. Let's take the first problem. Now, normally, we have been dealing with situations where we convolve to aperiodic functions, right? But now we'll take an example of convolving one periodic function with one aperiodic function. Yeah? So let's take the following example. We require to convolve the periodic function xt given in the following way. Where we describe xt by the following argument. Now, the question is that we wish to convolve this xt, which is periodic. So you see, here is to show one period. I have shown a dotted shape that this would then be repeated at every multiple of t. Yeah, and it is required to be convolved with the function ht, which is non-zero only over the interval 0 to t. Okay, and this is a straight line here. This is a straight line relationship, and it rises from 0 to 1, and therefore the slope is 1 by t. Yeah, the slope is 1 by t. So in fact we can write down ht here if we wish to. ht is simply 1 into t by t for t between 0 and 1, t between 0 and t, and 0 else. Yeah? Of course, this could be made less than equal to here. Now, you see, we've looked at how to convolve aperiodic functions. But when we convolve periodic functions, of course, we expect the length of the result is going to be infinite, naturally, because the periodic function has an infinite length. Even though this has finite length, finite support, right, the length of the result would range all over the real axis. But our interest would be to characterize the output, and we don't need to find the entire yt. We find only that part of yt which will tell us all about the rest, right? Now, how can we find out that part of yt which... So what do we do? How do we approach this problem? Let me put it to the class. How do we approach this problem? How do I convolve this with this? What should I do? How do I find out the result? Of course, I agree that we will... Now which one should we, we have a choice to fix one of the functions and to, reflect and shift the other. Which one should we reflect and shift? That's the first thing that we need to decide. ht, of course we need to reflect and shift ht because ht is of compact support. It's easy to reflect and shift. So let's write down the pattern for h of t minus lambda. So this would come at t, and this would be at t minus t. And of course this is, we can describe this function precisely. It can be described as this is, so you want h of t minus lambda, so as a function of lambda. Yeah. So this would look like t minus lambda by t into 1. Right, so this is how you would describe this. In the interval lambda between, lambda between t and t minus t. So this is h of t minus lambda as a function of lambda. Yeah, you agree with me? Is that right? Yes? This is how it looks? Yeah? Now of course now we can write this as x of lambda. It doesn't matter. We can call the variable anything. We can write this as x of lambda. Yeah, so now it's clear now. We wish to convolve this with this, so we out this shifted and translated version, shifted and reflected version. Now what do I do next? What should I do next to convolve this? Remember, we are dealing with a periodic function. Yeah, that's right. So we have a correct suggestion. Would you like to come and explain? Come. Yeah, now speak loud. Where's the mic? Yeah. Take it on and explain clearly, right? What you're going to do. Yeah. So you can first explain, right? What is your approach? Yeah.
Take convolution of ht minus lambda with x lambda, where x lambda is between 0 to t. Now if system is LSI, then if xt is periodic, yt will also be periodic. So we will find response of xt between 0 to t, and we will get, as yt is periodic, yt at entire t.
Good. Okay. Thank you then. Yeah. Very good. So, Devendra has given a correct approach. I'll just correct his phraseology. I mean, what he was trying to say. I think what he was trying to say is that you take only one period of xt, right? Take just one period of xt, all right? And assume that xt is not periodic. In fact, you may wish to constrain xt to the period 0 to t and convolve this with this, all right? Now, so let's talk about an x tilde lambda, which is just this without the dotted extension, right? And we now find the convolution of these. So we find the convolution of, we find the convolution with just this restriction, yeah? And then we know that xt can be obtained by taking this, shifting it by every multiple of t and adding up these shifted versions. Now, because the system is linear and shift invariant, the result of this convolution can also be shifted by every multiple of t, and the shifted versions can be added. All right? Now, what will be the length of the convolution? The length of the convolution, when you convolve just this with this, is going to be 2t. In fact, it will range from 0 to 2t. And therefore, now you will have a result of 2t, which needs to be shifted by every multiple of t, and these results added. So there's going to be an overlap of t between successive shifted versions. Right? Let's illustrate the idea. So let's convolve this with this. Let's get a feel of what kind of a convolution results. Of course, I won't write the expression. That can be written easily. Let's get a feel. Now, of course, the convolution, when you take this restricted version, the convolution starts only for t equal to 0. Right? So at t equal to 0, it starts from 0. Now the area starts building up until you reach t equal to t by, so you see, the area continues to build up until you reach t equal to t by 2. Yeah? Now at t equal to t by 2, what is the area? The area is what you get with half of this triangle. Is that right? So the area rises to half the triangle. Now, you see, sometimes it helps for us to have an insight into the nature of the result. If we don't need to explicitly evaluate the integral every time, we can get an idea, or if you want to sketch the output, we don't need explicitly to evaluate the expression. Sometimes we can get an idea purely from the nature of the result. Now here, this is a linear function. One is integrating a linear function. So one would have a quadratic result, right? One would have a quadratic result. So what we expect is that from 0 to t by 2, there would be a monotonically increasing quadratic, right? There would be a monotonically increasing quadratic. Now we need to decide, see, of course, monotonically increasing is no problem, but we need to decide whether the slope will increase or the slope will decrease. That will give us, so in a quadratic, both in a linear case there is no problem, there's only one slope. But when you have a quadratic, the slope could either increase or the slope could decrease. That could give you two different kinds of curves, a convex or a concave shape, right? So we need to decide between them also. So let's do that. Anyway, so let's, now what will happen? Will the slope increase here or will the slope decrease? What do you think? And why? Will the slope of the quadratic increase or will the slope of the quadratic decrease? Increase, right. That's right, because the area is increasing in greater and greater proportion as you move along the time axis. So therefore, the slope will also increase. That's, see, as you bring in more of this, more the rate of change of area is more also as you go along the triangle, and therefore the slope will increase. So how does an increasing slope look? Like this, right? So you have to choose either between this kind of a quadratic or this kind of a quadratic. So one would choose this kind of a quadratic, right? Because the slope increases. So anyway, what is the maximum area reached at t by 2? At t by 2, it reaches an area of how much? So, you know, right. So this triangle would have an area of t by 2 into half, right? So t by 8, right? So it would reach an area of t by 8 with a movement like this, yeah? Now what will happen afterwards at the point T? What would happen afterwards at the point, up to the point T? Now the area would, now what would happen? You see, would the area increase, would the area increase, the total area increase or decrease now? Decrease, is that right? The total area would decrease because now you have a negative part coming in, right? Because now you see, now this T moves beyond T by 2. So this part, actually what happens is, you know, of course, you know, this part of the area keeps coming in into this, but now the T moves here. So, you know, a part of this area will go into the -1 region. So that will contribute a negative area, right? It will contribute a negative area. Now, up to what point will the area, you see now, again here we can see, up to what point will the negative area go down? It will go down up to the point, so, you know, until the point T, the negative area will keep going down. In fact, the negative area will continue to go down even afterwards, because, I mean, the area will continue to go down even afterwards, because, you know, afterwards what will happen is that this will completely overlap only with the negative portion, right? But we need to, so in fact we need to divide this convolution into 4 segments here, right? The segment from 0 to t by 2, from t by 2 to t to 3t by 2, and from 3t by 2 to 2t, right? So in this region, expression, in fact we can write the, now I'll simply write down the expressions in each region, yeah? So in this region, the expression would be given by the integral of t minus lambda into -1 from t by 2 to t plus the integral of t minus, of course, t minus lambda by t into +1 d lambda, but the limits here run from t minus t to t by 2. That's the expression in this region. Okay? Because from t to t by 2 would overlap with this, and from t by 2 to t minus t would overlap with this. Is that correct? Is this understood?
small t less than capital T, then t minus 2 will be outside the upper restriction.
Oh. Yes, this is t by 2. That's right, yeah. That's correct. So here the limit needs to be up to 0. That's right. That's correct. That's a well taken. Here the second limit needs to be 0 because this entire interval is t and t is somewhere here, small t is somewhere here, this interval is t, so definitely this will go below 0. So you need to integrate only from 0 to t by 2. So that's perfectly correct, that's right. So Devendra is correct, there needs to be a correction here. This should start from 0 and go up to t by 2. That's because t is somewhere here, so this part is taken care of by this integral, okay? This part is taken care of by this integral. Upper limit needs to be up to t. T is somewhere here. Yeah, somewhere there. So it needs to be up to t. Yeah, is that fine? Now similarly one can write down the other regions, right? So one can write down the region here. Now what is the region here? How will you get the region here? T has come up to here and gone beyond. So now what is the expression for the convolution in this region? Well, this entire interval is subsumed, okay? So now how much is the integral? It's integral t minus lambda by t into minus 1 d lambda from t by 2 to t. All right? And there is a small tail here. There is a small tail here. So plus integral from t minus t to t by 2. T minus lambda by t into plus 1 d lambda. That's the convolution in this region. Okay? And finally, the convolution in this region will involve only the negative part of the function xt. Right? So that would be simply this expression. In fact, it would be just, this part of the expression. Is that right? It would be so for this part, it will be just this part of the expression. This part of the expression will be missing. Okay, it's simply t minus lambda by t into minus 1 integrated from t by 2 to t, and here you should interpret t as going from 3t by 2 to 2t. So there are 4 quadratic segments in this, in this convolution. I've written down the expression. So for the first one, of course, the expression can be written down very easily. The first one, the expression is simply 0 to t minus lambda by t d lambda. Yeah? And similarly, one can write the expression for the last one, which is simply this term, only this term. Right? It's very easy to do. Now, what I would expect is, now this gives you the precise way to go about it. I would encourage you to write down the integrals for each region and to sketch the behavior. And then to sketch the same or to verify the same sketch by looking at the fact that they are all quadratics and reasoning out whether the slope is increasing or decreasing in each region, right, as a function of t. So it's a good idea to verify. So of course this illustrates convolution by itself. Now what should you do to convolve the periodic xt with this? You take this result, shift it by every multiple of t and add up the shifted versions, right? Now when you shift it by t, this portion will overlap with this here. You shift it forward by t. This portion will overlap with this. In the next forward shift, of course, this portion will go outside, right? Also, when you overlap backward, then this portion will overlap with this, right? However, we don't need to evaluate the sum in the entire interval of 2t, because we know that the output is going to be periodic with period t. When you feed in a periodic input with period t to an LSI system, you get a periodic output also with period t. So you need to evaluate this sum shifted, and the result of shifting the input by every multiple of t and adding up the shifted versions only over an interval of t. So all that you need to do is to take this shifted by t to overlap with this, add up the sum, add up the result in the interval t to 2t, and repeat it in every interval of t. Right? That's the result. Okay? So that's how one would convolve the periodic xt with ht. Now there's another way to solve the same problem. Yeah? You see, you know that the result is going to be periodic with period t. So what one can do is to consider evaluating the convolution only over an interval of t. Right? So you may then consider only this region of xt. Of course, xt is repeated periodically on either side afterwards. But let's consider only this part of xt, right? And let's evaluate the convolution of. So this is x of lambda. And of course, we have h of t minus lambda. Now we evaluate this convolution only for t going from here to here with this function x drawn. That will give us the same result. Yeah? Because once we find out the convolution in the interval 0 to t, then it repeats itself after every multiple of t. So that's another approach to doing the problem. I would encourage you to solve the problem also by that approach and check that the answer is the same. Right? All right. Now taking this idea of periodic functions further, let's consider another problem where we wish to convolve a special kind of periodic function with an aperiodic function or signal. Let's consider a train of impulses. So we have the following function. We have a train of impulses. A train of impulses is a set of impulses located uniformly at a certain interval of spacing. So let's assume that we have a train of impulses located like this, all of unit strength. I'm sorry, my drawing, yeah. They are all of the same height, so all of them enclose an area of 1. Yeah. Now we wish to convolve this xt. This is xt. So in fact we have an expression for xt. What is it? Xt is summation k going from minus infinity to plus infinity of an impulse located at k times t. Is that right? This delta t minus kt is an impulse of strength 1 located at t equal to kt. Therefore, when you add them, you get a train of impulses. Needless to say, this is a periodic signal with a period of t. Yeah? Now, we wish to convolve this with another ht, which looks like this. Okay? This is the second function ht. We wish to convolve this with this. To evaluate the result, we shall now make use of the property of linear shift invariant systems. So we'll think of this as an input to the linear shift invariant system and this as the impulse response. Now, by using the property of linearity and shift invariance, we can find out the response to one of these impulses. In fact, the response to, for example, this impulse is just ht. So all that we need to do is to take ht, translate it by every multiple of t, and add up the translated versions. Right? Now, there are two possibilities here, and that's what I'm going to illustrate now. The two possibilities are that these, see, what is going to happen is that when we translate this, now let me do that, let me translate this and add them up. So in fact, we can even write down, the expression for yt in a closed form. Or not closed form, but in a series form. So yt is in fact summation k going from minus infinity to plus infinity h t minus kt. Alright, that's the expression. But let's sketch this expression. Now what I'll do is, I'll take this ht and put it on the same graph here. Or maybe I'll draw the graph here below. That's easier. So you see at every, now let's take the case where t is greater than 1. Let's take the case where t is greater than 1. Okay? So the impulse at 0 will result in this. In fact, not just greater than 1, we need it to be greater than 2. So let's take the case when t is 2. Okay? Now, when you shift this forward by t, you are shifting it forward by a number which is greater than 2. So, visualize this being shifted forward by t. Now, our difficulty, see, in evaluating the result, our difficulty is whether the shifted version will overlap with this or not. When will it overlap with this? When t minus 1 is greater than 1, right? So overlap occurs when t minus 1 is less than 1. Yeah? That is, t is less than 2. So for t greater than 2, greater than equal to 2, no overlap. Is that right? Is that right? No problem. Now it's very easy. So you see, if we consider the case t greater than, in fact we can take greater than equal to 2, no problem. Yeah? When we take t greater than equal to 2, what will be the nature of the result? It's very simple. It will simply be this triangle repeated at every multiple of t. So it will look like this. Yeah, minus t, t, 2t and so on, repeated at every multiple of t. This is minus 1, this point would be minus t plus 1, this point would be minus t minus 1, right, and this point would be t minus 1, this point would be t plus 1, and so on. Okay, no problem. So this is the case when t is greater than or equal to. In fact, when t becomes equal to 2, these points just touch. Right? The points just touch. Now what happens when t is less than 2? Then we can consider this region. Consider what happens when t is less than 2. So in fact, again, we realize that we have a periodic input with a period of t, and the output is bound to be periodic with period t. So we need to consider only the interval, only an interval of t, right? Only an interval of t. So we can consider what happens in the interval 0 to t. So well, let's take the case of t less than 2 now. So we have this shifted forward by t, and t is less than 2. Right, so here is 1, and t minus 1 is somewhere here. Now, of course, we need to add up these two, versions. I mean, this is going to get added to this. Now, here again, we must make use of our understanding of functions. These are both linear segments. So when you add them, the segment will also be linear. So we might evaluate the result only by looking at the endpoints, right? So what will the endpoints be? At this point, the sum will be this. And at this point, the sum will be this. So in fact, the result is going to be this segment, then a flat segment, then this segment, and so on. Yeah, this is how it's going to look. So between the points t minus 1 and 1, it's going to be flat. Right? Between the points t minus 1 and 1, it's going to be flat. Yes? That's right. Here we are assuming that t is greater than 1. In fact, if t becomes, let's take the case when t equal to 1. What will happen when t equal to 1? The entire thing will become flat. So we said it's flat from t minus 1 to 1. So it will be flat right from 0 to 1. Right? So in fact here, you can say it's greater than, so we are taking the case where it's greater than or equal to 1 and up to 2. Now what will happen when t is less than 1 again? Yeah? That's right. So if t is less than 1, and the situation is like this. We have this, so it's shifted by t, so it's somewhere here, right? So t is less than 1. Let's say it's somewhere here. So now what will happen? Now you will have to consider the following regions, right? You need to evaluate only in the region 0 to t. Of course, remember the output is going to be periodic with period t, right? So you need to evaluate only in the region 0 to t, but one must be careful. You see, now the backward shifted version will also come into play here. right? Because when you shift and add, you must, in a region of t, look at all the shifted versions of the function which add, right? So, if you look at the one that is shifted backwards, how will that look? So this goes somewhere here, all right? Now t is less than 1. So let's draw that. So now maybe what I'll do is I'll solidify this. So now so without any confusion, I think we understand that this was the original ht, right? This what is now drawn as dotted is the version of ht translated forward by t, right? So now I'll solidify that because I want to bring in one more, right? So this is the version of ht shifted forward by 1. I wish to draw the version shifted backward by t, and t is less than 1, so maybe it will come somewhere here. And it will also transgress into this region. So you will have another version of this which will overlap like this. Okay, so now in this region 0 to t, we shall have to consider a sum of all these segments. Okay, we will need to consider a sum of all these segments. Do we need to consider any further backward shifted versions? We may. That's right. As t tends to 0, the number of segments that we will need to consider will start going towards infinity. Right? So you have to consider more and more segments. Or would you? No, here t is less than 1. Here t is less than 1. Now you can see, you can visualize the original function ht. See, as you just visualize, if t is very small, you are shifting it infinitesimally. If t is very small, you are shifting it infinitesimally, and you are adding up infinitesimally shifted. So in the limit, what will happen is all these ht's will, if you take t equal to 0, then just visualize, t equal to 0 means the same ht is added upon itself an infinite number of times. So you need an infinite number of segments. So as t becomes smaller and smaller, you will start needing to consider more and more segments, right? So it becomes more and more complicated. All right? Anyway, so this was to illustrate what happens. Now, in fact, this kind of a convolution is extremely important. Here we are doing it in the time domain. A similar convolution will be extremely important to us in the frequency domain later on, right? When we talk about sampling of functions, then we'll need to use this kind of convolution implicitly, right? So let's keep in mind how to work out a convolution like this with, where you have a function, a continuous function, or, at least a function with a finite number of discontinuities convolved with a train of impulses, right? Now I take another question. We are given that a function xt has the following area under xt. So the integral of xt from minus infinity to plus infinity converges and is equal to ax. We are similarly given the integral under the function ht. Both of them converge and are respectively equal to ax and ah. We are required to find out the integral under the convolution of xt and ht. Right? So we are required to evaluate integral yt dt from minus infinity to plus infinity, where yt is xt convolved with xt, with ht. Now this is an extremely simple problem if we write down the convolution integral. So let's write down the convolution integral. The convolution integral would be x lambda ht minus lambda d lambda. And we wish to integrate this dt. Alright? Now in fact, one can see that the operator dt acts only on ht minus lambda. So one can bring in this operator to act here, and since the integral on ht converges, right? So you may write this as integral x lambda integral h t minus lambda dt, right? And then integrate with respect to lambda. Now you see what t minus lambda, for a fixed lambda, it's just a shifted version of h. Now shifting doesn't change the total area function. You're calculating the total area. In fact, one can make a change of variable if you like. Put t minus lambda equal to 5. So therefore, this is simply ah. The inner integral is simply ah. That's a constant independent of lambda. So now we have ah times integral x lambda d lambda, which is simply ax. So it becomes ah into ax. The answer is as simple as that. Right? So therefore, it's a very interesting result that we have. The convolution of two functions has an area given by the product of the areas under the functions which are to be convolved. Okay, that's a very interesting result and is sometimes very useful, right? So we shall take up a few more problems in the lecture tomorrow. Yeah, we'll stop here, take up a few more problems in the lecture tomorrow. Thank you.